Good morning. Hello. Happy Tuesday. So as you can see behind me here, we're going to be working on organic chemistry today. I hope you all are doing okay. So I just pulled up Discord in case you all had questions, and like a bunch of messages just came in. So I don't know if it was my phone ran an update or something and it shut off. But if you've been trying to reach me via Discord for the last few days and you haven't gotten a response, it looks like I'm just seeing those messages now. So I will get back to you, but you can always ask again if you want. Hi, Alyssa. Hey, Monica. Good morning, Renette. Good morning, Maria. Good morning, Daisy. All right. So as you have certainly heard, Harper is going back to fully online. We can't do labs anymore. Um, we possibly could have still done some makeup labs this tomorrow if originally, but with everything going on, and I know some of you have gotten notice that there was a positive test in one of the sections, so we can't go in the lab tomorrow anyway. So that's it for our labs for the rest of the year, which is unfortunate. But we got most of it done, and honestly, um, I'm pleasantly surprised at how much lab we got to do. I thought everything was going to get shut down a lot sooner than this. So we did what we could. We have the acid-base virtual lab this week, and then after Thanksgiving, we'll have an additional virtual lab to work on together for talking about some biochemistry, biological molecules. Hi, Jennifer. And that'll be pretty much it. I mean, we're getting close to the end here. We've got a couple more chapters, some organic chemistry, some biochemistry, and then the final exam, and we're done. So, um, another thing I wanted to mention, since we don't have labs on Wednesday anymore, it kind of frees up some time in the afternoon. So if you want some extra help, if you want to meet with me online to go through some homework or to answer questions, that chunk of time is good because obviously we all had that scheduled and now we don't. So if you want to meet with me, let me know, and that might be a good time to do some studying and get some questions answered. All right, let's talk about organic chemistry. Let's set up here. Okay. So first of all, you've probably heard of organic chemistry. You've probably heard the phrase. Some people find it kind of scary, like you may have heard rumors from other people that organic chemistry is this really, really hard class that um, something like that. I don't think that's really accurate, although it's true that it has often in the past been taught as this sort of like weed out class that's really hard. But what it means for us is it's just really chemistry of molecules based on carbon. So instead of all the inorganic stuff like the ions and the salts and the inorganic covalent compounds with all of those elements from that non-metal section of the periodic table, organic chemistry focuses on molecules that are primarily built up from carbon. Now they have other elements in them too: hydrogen, oxygen, halogens, other stuff, sulfur, but primarily we're looking at carbon-based molecules. And the reason that's important, the reason it kind of gets its own category, is because chemistry that's limited to these types of atoms tends to be fairly predictable. So you can look at the structures of these molecules, eventually you'll be able to, and pick out different parts and say, okay, this part of this molecule is going to do these kinds of reactions, and this kind is going to do this. It's almost like some sort of a like kids connecting toy that has particular ways that it connects to other things that are very predictable, and you can kind of see how two pieces might connect just by looking at the parts. So a couple things just to review from before in terms of organic chemistry that we'll need to know is some of our bonding. So just to review, carbon generally makes 4 bonds. That's kind of our basis for organic chemistry. And other than in some less stable compounds, that's going to be a pretty strict rule. So we're going to be able to build up these compounds just from knowing this. And we've seen a lot of these compounds too. Hydrogen makes 1 bond. So that allows us to build up these types of compounds. Like if we want to make, let's say, a 3 carbon molecule. Write that down here. With only carbon and hydrogen. There's a limited number of choices that you can actually make a molecule like this. So you can go like this, and get what is that, C3H8. You could add some multiple bonds, so you could put like a double bond in there. And we've done some of these before. You could kind of connect it back on itself, make like a triangle. That's called a cycloalkane. We'll talk about those later. But the point is, there's only a limited number of ways that you can do that because we always have to be following these rules. So that's what we're going to talk about first is just these basic organic structures and some different ways of drawing them. Then we're going to add some other elements in there and talk about functional groups, which are how these things react with other molecules. And then we'll actually see some reactions. Yeah, so good question, Daisy. It doesn't matter how many hydrogens we put. I mean, yeah, right. So you could have molecules with more or fewer hydrogens depending on how you connect things together. If there were a specific formula, then it would be back like when we were talking about Lewis structures, and you have to use that certain number of elements. All right, so the first class of materials or of molecules that we're going to look at are called the alkanes. Alkanes are molecules made from carbon and hydrogen only. With no multiple bonds. So no double bonds. So of the ones we drew up here, this top one and this bottom one would be considered alkanes. Now what we're going to do is we're going to set up a table of the alkanes, and we're going to kind of fill it in. And at first we're going to just fill it in together, and then I'm going to start leaving blanks and see if you can fill in the blanks, and we'll talk about what those different columns mean. All right, so first we have the molecular formula. Going to be our first column. Then the name. And then we're going to have something called the condensed formula. And then finally, I got to leave a little more room here. And then finally, we're going to have the what we call the line structure. which is sometimes called, well, let me see what it's called in the actual, yeah, sometimes called skeletal structures. There's some different names, but you'll see what I mean. So we don't know what these things mean yet, but rather than give you a formal definition, I think it makes more sense to look at some examples and then talk about the definitions. All right, so our first simplest alkane has the formula CH4, because carbon needs 4 bonds, so the smallest possible alkane that we can have is 1 carbon with 4 hydrogens around it. And that one is called methane. Its condensed formula would also be CH4, and it doesn't really have a line structure. So we're just going to leave that blank. Well, we shouldn't leave it blank. We'll just say none. Too small. Okay, next one is going to be C2H8. Whoops, not H8, sorry. C2H6. That one is called ethane. Its condensed formula is CH3CH3, and its line structure is just a line. So don't worry too much if this doesn't make sense yet. As we get some more examples, you'll start to see some patterns, and we'll talk about it. All right, our next one is C3H8. The name is propane. The condensed formula is CH3CH2CH3, and the line structure is this. All right, so let's pause a moment before going on to the next one and think about what's happening. So in each case, the molecular formula keeps increasing by 1 carbon and 2 hydrogens as we go up by members of the group. If we go back up to what we drew before, this is an example now of propane. You can kind of see how that works, that if we had only 1 carbon, we would need 4 hydrogens around it. If we have 2 carbons, there'd be 3 around one and 3 around the other. And now that we have 3 carbons, we've got kind of like the outside ones have to have 3 carbons around them because that gives them 4 bonds. And the inside ones only get 2 hydrogens because, again, if they had a third one, there would be too many bonds there because carbon can only have 4 bonds. So all of this stuff is based on this idea that carbon can only have 4 bonds. So now let's look at these other 2 new columns with the new terms here, the condensed formula or condensed structure and the line structure. So notice that when we start talking about these bigger and bigger organic molecules, the molecular formulas that just tell you the number of each atom become less and less useful because as we get bigger and bigger, if we actually want to know what C3H8 looks like, we have to figure it out. We have to draw it out. So it becomes a whole lot more obvious, I think, to look at something like a condensed formula that tells you exactly how this thing is laid out. Now, one thing we do need to know about the condensed formula here is that this is not laid out in a straight line for all the atoms. The carbons are connected in a straight line, but we have to know that carbon only has 1 bond and carbon only has 4 bonds and hydrogen only has 1, so that we know that when we say CH3, what we're really saying is those 3 hydrogens are connected to this carbon. When we say CH2, what we're saying is that those 2 hydrogens are connected to this carbon, and so on. So we're not saying CHHHC, like in a straight line. We have to know a little bit of chemistry to know that those hydrogens go around the carbon. And then this is the line structure. And again, I'm going to leave that for a second. We'll talk about it shortly. This time, I want you to take a guess, grab some paper. I'm going to tell you that the next formula is C4H10, that it's called butane. And then without looking anything up, see if you can guess the condensed formula and the line structure. Just write it down on your paper. What do you think that would be? All right. You had a chance to get something down there. So one way you can solve this problem is by actually going through and building the whole Lewis structure there. Yeah, I got some good guesses there. So let's look at it. One way you can do this is by actually solving out the Lewis structure. So you can draw your 4 carbons, and you can put the hydrogens all the way around. Like that. And then you can kind of count it out and say, okay, this carbon has 3 hydrogens, this carbon has 2, this carbon has 2, this carbon has 3. So that means that our condensed formula would look something like CH3, CH2, CH2, and CH3. So that works, right? You can already see, I think, why we're moving away from Lewis structures when we talk about organic molecules. Because as these things get bigger and bigger, it just becomes really time consuming and annoying to draw out every single atom every time. So ways of condensing the structure, making it a little bit smaller, making it a little bit faster to write. And if you can imagine, well, like those of you who typed it into the chat, it's a whole lot easier to type something like this, which is true in Microsoft Word or whatever, than trying to actually draw out this structure. So this is the correct condensed structure. The other way you could do it is by following the pattern, by recognizing that every time we add another carbon, we have to add 2 more hydrogens with it so that every carbon still has 4 bonds. And then if you got a chance to try the line structure, unfortunately I can't see what you did over chat, I don't think, but hopefully maybe you got something like this, and it's probably time we start looking at what that actually means. So just those of you who did try it, did you get something like this for that line structure? Did you add like another line from this one? Okay, good. So let's dig into this a little bit and see what's going on, especially for those of you who didn't really understand this. Well, so it doesn't actually matter. You could have put another line somewhere. Let's talk now about what those line structures actually mean. Yeah, down uh your rules are a little too strict. So let's go through them now that we have some examples. So for line structures, um, and let's use butane, that last one, as an example. We assume for a line structure that there are carbon atoms at each end of a line and anytime 2 lines come together in an intersection. So let's also draw out the Lewis structure for butane here so you can kind of see what's going on. So if we think of this as 4 carbons, I'm just going to add numbers to them so we can count them. 1, 2, 3, 4 carbons in a line. That's butane. The line structure represents those by having carbon atoms here, 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 and here. So that's carbon 1, that's carbon 2, that's carbon 3, and that's carbon 4. It's not so much that each line is a C, but where the lines connect. So every like point, every vertex, every intersection is a carbon, including the ends of the lines. So there's a carbon here, 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 and here. and the line still represents the bond between those two carbons. So the other thing that you see missing here is hydrogen, right? No hydrogen's shown. And the reason that works for these structures is because of that 4-bond rule for carbon. So because carbon must have 4 bonds here, yeah, we'll look at the hydrogens on the line structure. Because carbon must have 4 bonds, we can assume there are enough hydrogens to fill that valence or that requirement. So let's look at how that works. If we wanted to know carbon 1 right here, if we wanted to know how many hydrogens were on carbon 1, we would say, all right, well, this represents a carbon, and we know that carbon has to have 4 bonds. 1 bond is shown, the bond that goes between this carbon, carbon number 1, and this carbon, carbon number 2. So then there must be 3 more hydrogens here so that that carbon has in total 4 bonds. So we're kind of like assuming that there are 3 more hydrogens here that are not shown, so that that carbon has a total of 4 bonds. If we move over to carbon number 2, we look at that carbon and say, okay, well, we can see that there are 2 bonds shown, the one to carbon 1 and the one to carbon 3. So in order to fill that valence and get up to 4 bonds, we need 2 more hydrogens here. So there are 2 hydrogens that are not shown there, and we can see that that must be a CH2. Then 3 is going to be in the same situation as 2. So 2 bonds shown, which means we need 2 more hydrogens. And then on 4, we have 1 bond to carbon, and that means we need 3 more bonds for the 3 hydrogens. Yeah, good question, Jennifer. Are there exceptions? Seems like there's always exceptions in chemistry. I mean, kind of. So we're going to talk about some of them. We'll use a different color here for our exceptions. It's not really an exception, but this is only for carbon and sorry, we're not going to be able to see this. The hydrogens connected to carbon. So what does that mean? Let's look at another example. So I'm going to draw a Lewis structure, and we're going to convert it to a line structure. And this time we're going to add an oxygen in there. All right, so here's what you do. When we draw our Lewis structures, we usually draw them straight. 90-degree angles. We often do that. But as we also learned, that's not the real shape of the molecules. So for instance, carbon has 4 things connected. It's going to have that tetrahedral geometry. So that's one reason why the 90-degree structures get converted to this zigzag look, because the zigzag really better approximates the angle, the real angle that would exist of those bonds. But also because now that we're taking the atoms away, we need the zigzags to show us where the individual different atoms are. If we just drew a straight line, we wouldn't have any sense of how many atoms are inside that straight line. So what I do when I start drawing a line structure is I first need to count up the number of carbons. 1, 2, 3 carbons. And that tells me how to make my initial zigzag. So if I'm going to convert this structure into a line structure, I take 3 carbons and I make a zigzag. Now, it doesn't matter if I go like this or if I go like this, or you could even do it sideways. Yeah, the oxygen would have lone pairs here. So it doesn't matter what orientation you put this thing in. Any kind of flipping around, whatever, those are all still the same structures. I'm just going to stick with that first one because that's what I drew first. But it can also be helpful there to renumber, draw new numbers so you can see what you're talking about. So we've got 1, 2, 3, 1, 2, 3. Now, carbons numbers 1 and 2 only have hydrogen connected. And since we don't draw hydrogens in the line structure, we can just leave it as is. We don't need to connect anything else off of carbons 1 and 2. But carbon 3 has 2 hydrogens, but also an oxygen with a hydrogen. And because of this last rule, we can't abbreviate other stuff. And the reason is other elements. And the reason is that other elements are not as predictable in their bonding patterns as carbon and hydrogen. So we can't just say O, because O doesn't always have 2 bonds. We think of it as commonly having 2 bonds and 2 lone pairs, but it's not always true. So when we draw O, we also have to draw anything that's connected to it. So I'm going to draw an additional line here connecting to the O, and then the H connected to that O as well. Now, the fact that I drew it off to the right versus down or something, that's just arbitrary. You could have drawn it down. You could draw it wherever you want. I like to kind of keep that nice zigzag in a line, so I just kind of keep it going this way. A couple things to note then. This is the complete structure. You can draw lone pairs on the oxygen here as well, but you don't actually have to. Since we're mostly focused on the structure now and how the thing is put together and how it looks, you'll see line structures that have the lone pairs and some that don't. It won't be so much as like in a Lewis structure where you absolutely have to have those lone pairs there so that you can talk about the geometry and all of that. Sometimes we'll put them there, sometimes not. But another thing to note here is this kind of looks at first glance like 4 carbons, 1, 2, 3, 4. But because that oxygen is there, this end of this line is not a carbon. That's just connected to the oxygen. So it is important to have an additional bond or a line that goes off to whatever other atom is connected. Let's try another one. This time we're going to introduce a double bond as well. And then we'll add a chlorine. So this molecule will be something like that. And we're going to start the same way, numbering our carbons, making sure we keep track of everything. We've got 3 carbons again. 1, 2, 3. The difference now is there's a double bond between carbon 1 and carbon 2. So the way we draw that is just by adding an additional line like that between carbon 1 and carbon 2. And then we have to account for this chlorine coming off the right side. Now notice here I drew the chlorine as coming down. But in the structure itself, if you recall from back when we talked about that stuff, how you draw, where you put those things doesn't matter because single bonds freely rotate. So whether we draw the Cl like this or like this, that's the same thing. And this is actually one of the trickier parts of what we're going to start seeing is that, oh yeah, there's too many hydrogens here. Thank you. Sorry. One of the trickier things we're going to see is being able to identify that these two are actually the exact same molecule because they only differ by rotation around the single bond. And one way of thinking about that is using those numbers and saying, okay, both of these are a chain of 3 carbons with a double bond between 1 and 2 and the chlorine coming off of the third carbon. So there's really no way of distinguishing one or the other. They only differ by rotations around that bond. So now thinking about the hydrogens, now that we've added some more stuff, do those rules that we originally talked about when it comes to hydrogen still apply? And so let's check and see. So now when we look at carbon number 1, we would say, well, this carbon shows 2 bonds connected to carbon number 2, a double bond. And that would mean that it needs 2 more bonds, so we need 2 hydrogens there. And in fact, it does have 2 hydrogens. Carbon number 2 has 3 bonds shown, 1, 2, 3, and therefore it only needs 1 more hydrogen, which we see there, which I drew wrong at first, but there should just be 1 hydrogen there. And then over at carbon number 3, excuse me, over at carbon number 3, we've got bonds shown to carbon number 2 and to the Cl. So then we have 2 more hydrogens there. And that's what we have here as well. All right, so that's the basic idea of going back and forth there. We're going to do some more practice with that. But I want to try finishing our table from up here. Well, not finishing, but I guess going a little bit further. We've got methane, ethane, propane, and butane. These are the 4 that have kind of weird names. Weird in that it has nothing really to do with the number of carbons. It's just a name given to that structure. So methane, ethane, propane, butane, you just have to remember that those apply to 1, 2, 3, and 4 carbons. The rest of the series gets much easier because it uses standard prefixes like we learned before. So this time, I'm going to give you the name, and I want you to draw the condensed structure and the line structure for the members of the series. And I think you can do it. So I'll give you a hint. We ended up here at 4 carbons, and we're going to continue starting with 5. And the names are going to be pentane, hexane, heptane, octane, and they keep kind of going. We've seen these prefixes before. The next one would be nonane and then decane. But let's just try these 4. I'm going to turn my screen off and fill them in on my own so that when I bring them back up, you can see them, but I want you to try them also. See if you can draw a condensed structure and a line structure for each of these. All right, let's see. Don't worry if you didn't finish them all. You can pause the video for a minute if you want, but it'll be fine. Okay, so here's what I got. Now I cheated a little bit. I didn't really cheat, but I used another shortcut that I didn't tell you about because I didn't want to write all those CH2s. You can see the condensed structures here and the line structures. And then, especially when you get to these longer chains, it's always a good idea after you draw it to make sure that you recount it because it's easy to just put in an extra one. So we got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Now with the condensed structures, for pentane I drew it all out, CH3, CH2, CH2, CH2. For hexane, I got tired of doing that, so I used this shorthand where I use parentheses to say that there's a CH3 and then 4 CH2s and then another CH3. And then for heptane, CH3, 5 CH2s and a CH3, so 7 carbons total. So that's something you can use also, and we'll use that a lot when we get into some really big molecules like lipids and stuff like that. All right, any questions about those so far? Another thing I want to review from before kind of are the shapes, but specifically with regard to these types of molecules. So please recall that carbon, when it makes 4 bonds, does not have a planar structure like this, but has a tetrahedral 3-dimensional structure that we often express like this, where we show 2 hydrogens that are in the plane of the screen, and then one that's coming out toward you, and one that's going back away. And we use a wedged kind of bold line to show that that's coming out of the screen, and then a dashed line to show that that's going back into the screen. That structure is called tetrahedral. If I spell it correctly. And it comes from that Vesper theory, that idea that the atoms and the electrons always want to push each other away as much as they can, and that's the most efficient way for them to do that. The other thing to know that we'll get into is when we look at double bonds, even though we might draw them in a Lewis structure like this with 90-degree angles, we also know that when there are 3 atoms or 3 electron groups around an atom, that the geometry it adopts is called trigonal planar. So we should also recognize that when we draw something like this, if we really want to express that better in geometrically, we can show those 120-degree trigonal planar angles. So it's not that the whole molecule is trigonal planar. When we look at bigger molecules, we're looking at each individual atom as having a particular geometry. And in this case, those are both trigonal planar. So that influences geometry a little bit with these bigger organic structures. And that brings us to the next topic, isomers. So we talked a long time ago about isotopes, which are atoms that have different numbers of neutrons but the same number of protons. Isomers are molecules that have the same molecular formula but different, and we'll use the word connectivity. So it's a different structure. And isomers are different molecules. they're not just different forms of the same molecule, they're actually different molecules. They have different physical properties like boiling points, melting points, reactivity, stuff like that. All right, so let's look at what this might be. If we take a molecular formula like C4H10, butane, one thing we can do is see how many different isomers we can make. So these are different molecules that all have the formula C4H10. So here's one. This is one isomer of C4H10. That's the one we drew before. See if you can find another isomer of C4H10. There is only one other molecule that you can draw that follows the rules and that has the formula C4H10. I don't know how you're going to be able to communicate it through the chat at this point, but just give it a try and then I'll show you. While you're doing that, I want to also draw the condensed structure and the line structure for this one. Okay, well, let's start by talking about what is wrong, what doesn't work, and what is often a first try. So if we were in person here, it would be great because I could walk around and kind of see, and we'd be working in groups and trying to find these different structures. But what I often see a lot of people try first is something like this. So why is this structure not an isomer? Why is that not an isomer? Any ideas? What's wrong with that one? Why is it not an isomer? Yeah, that's exactly right. Thank you. It's not a different molecule. It's the same as the first. It only differs by rotation around this bond right here. And we know that single bonds can rotate as much as we want. So if you had like a model kit, which would be also nice if we could do that in person, you could put these things together and you could spin them around and you can see that they are always the same. So not an isomer. So the only way you can make an isomer here is, and one way to think about this when we're making isomers is imagining this as a model kit. Imagine you had some carbon pieces and you connected them together in a line of 4. How would you make a different molecule than the first one that's not just being able to spin around and rotate. Well, the way you'd do it is you'd actually like pull off one of the pieces and try to connect it somewhere else in a way that made something different. And that's exactly how you find the answer here, the isomer here. We pull off that carbon and we connect it in the middle instead. And now if we add our hydrogens again, we find that we do have an isomer. We have something with the same formula, the same number of carbons and hydrogens, but it now has it is connected in a different way that we can't just spin to convert. Well, it would always be in the middle. It depends on the structure. So this is the only possibility. We're going to look at an example in a minute where there's some more possibilities. Um, but so the issue, there's also a question about double bonds. If you try to add a double bond, let's do that. Well, okay, so let's not do it there because we already put that back in. But we can do it over here. There it is. So if I had something like this, and I said, oh, okay, well, I'll just put a double bond. That'll make an isomer. Here's the problem with that. Once we start adding our hydrogens back in, because there's a double bond there now, we can't put as many hydrogens because those carbons need 4 bonds and the double bond counts as 2. So now, instead of being C4H10, this molecule is C4H8. And so it is not an isomer because it has a different formula. Okay. So now that we've drawn this one, this is the only other isomer for butane for that formula. Let's look at the condensed structure and the line structure, because what we see here is something a little different than what we've seen in the past. It's not just a straight chain. So we can't just write CH3, CH, CH3. It's going to get confusing. So there's 2 solutions here. There's 2 ways to write a condensed structure when it starts branching off like this. One way is to just reduce the hydrogens down onto the carbons, but keep the lines between the carbons. So we could write this as CH3, CH, CH3, and then CH3. That still does the job of making it easier to draw and not having to draw out every single hydrogen, but then we can still see the structure and it's still clear how it's connected. If you were really stuck, like you're trying to type something into a chat window or something, there's still no way to really express this. And so then the way that that's done is with parentheses. So another way, if you truly wanted to write this in a line, you could go CH3 taken twice, CH3. Now this one can be a little bit confusing because you need to know something about chemistry. Often when we see this parentheses 2, we just think 2 in a row. So in this case, you would need to know that you can't have a CH3 in the middle of a structure because that would be too many bonds on the carbon. The fact that there's 2 of these means they have to both be coming off of this carbon, this middle one. So oftentimes these like very linear condensed structures are not as popular because they are a little bit more confusing. And then finally, if we wanted to draw a line structure, we need to express this shape, which is really, we can think of as 3 carbons with a 4th one coming off of the middle. And so we might draw that like this, or move that up a little bit, or some rotation of that. And then just to make sure everything is accounted for, right, we've got our 4 carbons, and we've got our 4 carbons here. All right, so for our next test of this, and this will probably go into next time also, Yeah, let's look at that condensed formula again. So in this case, we've got two CH3s, a CH, and a CH3. We can't put those two CH3s directly in a row because we'd get this. And this carbon now has 5 bonds. Carbon, carbon, 3 hydrogens. That's 5 bonds, so that's no good. This carbon only has 3 bonds. Carbon, carbon, hydrogen, so also no good. So that kind of a structure doesn't make sense with the rules we laid out before. I tried to erase it. So that means that when we say CH3 taken twice, what we really mean is there's 2 separate CH3s that are both then connected to the CH, which is connected to the other CH3. So that's what that CH3 means in that case. All right, so now here comes a bit of a challenge, and I think we'll probably just stop and come back to this next time. But at some point in the next couple days, to practice this, see if you can find isomers of C6H10, draw them as condensed structures, and draw them as line structures, and really, really, really resist the urge to look them up. Because yes, you could do a quick search, and you could find all the isomers of C6H10. Easy. The point here is, can you figure out how to put them together? Can you build isomers of C6H10? And remember, they have to all have that formula. So they all have to have 6 carbons and 10 hydrogens. And they have to be different from each other. So you have to think about rotating them, flipping them around, and so on, so that you can find them. I'll give you a hint. There are 5. One of them is pretty straightforward, just the straight chain, right? C, 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 the one that we've already looked at that we called hexane. But there are 4 other ones that are different from that and different from each other. And over the next couple days, while you're doing your other stuff, see if you can find them. All right. So beyond that, if there's any other questions, go ahead and type them in now. Otherwise, we'll meet back on Thursday to talk about functional groups and reactions. There's some nice mastering chemistry practice for you. There's also a practice for these line structures that gives you the skeletal or line structure and the expanded or Lewis structures. Let me show you what that looks like of some pretty big molecules here. Hold on, I gotta put it up on the screen here. There it is. So you can see there's some nice practice with some big fancy molecules, and you can try to build these in line structures, and then there's another document that allows you to just to see what they are supposed to look like in those line structures, so you can check your work. You can also do that. You can also do it backwards, and you can look at the line structures and find all the carbons and hydrogens and make sure you have them all accounted for, and then flip back to this to see all the rest of them. So that'll give you some good stuff. Question: the final exam, the new topics? No, final exam is comprehensive of the entire class. I should also note, we'll talk about this when we get closer to it, but the final exam, it may have questions on it that you don't know, that you can't figure out. The final exam is a standardized exam. It'll be in Blackboard, but it'll be a standardized multiple choice exam that all of the Chem 100s take together. So it may not exactly match with our objectives, but it will be curved accordingly. So the other exams, whatever you got, your percentage is just your percentage. The final exam, because there's so many people taking it, we can look at statistics and use averages and adjust the scores accordingly. So there may be some questions on that final exam that you're like, what is this? We never talked about this. That's okay. That'll be accounted for in the scaling. All right, so happy structuring, and if you want some help or like we're looking at these isomers or whatever, definitely let me know so we can schedule some time either tomorrow afternoon or other times also. Those of you who have seen me, we can always find some time. And yeah, stay safe, stay healthy, and I'm sorry we won't get to see each other in person again this semester, but I'll see you online on Thursday. Bye, everybody.